Is it recorded? Yeah. Perfect. So if you look at this equation, it's very difficult to solve an equation like that for y. So you need a way or a tool, an approach, however you want to think about it, to do a derivative of equations like this when you can't get y by itself. Well, what you do is follow all the laws of derivatives we've talked about. Product rule, quotient rule, the different patterns, and you just do the derivative of this thing, use chain rule, using this thing. You just have to keep in mind that every time you take the derivative of a variable, what you're taking it with respect to. So for instance, we really haven't talked about this, but if I was going to do the derivative of x squared, we've talked about this a little bit, it would be 2x times the derivative of x, which is x prime. But what is the derivative of x? So we don't write that. Now, another way you could write the derivative of x or x prime with respect to x, because we're trying to figure out how fast y changes when x is changing. You could write it like this: the change in x with respect to the change in x. Well, however much x changes is exactly how much x changes. So these two numbers are going to be the same, and you still get 1. You see a lot of this kind of notation, though, the fraction notation with derivatives, still 1, and you're left with just that. And then you go to the next one.
So, do you have a simple definition for what in respect to means?
Slope.
Okay, so the
How about, could I convince you, or in Algebra 2 or Algebra 1, did y'all talk about independent and dependent variables?
yes.
Right, like the independent variable controls what happens to the dependent variable. When I say with respect to, what I mean is depending on how much the independent variable changes.
Okay.
Does that make sense?
Yeah. Do you have an example?
Yeah. If I'm driving down the road, my position is changing with respect to time. Right? If you freeze time, my position cannot change. Right? So time is the independent variable. When I do the derivative of position, I'm doing the derivative of position with respect to time.
Okay. So what about in cases where there are 3 variables? Because
Let's say this was a particle moving in 2 directions, an x direction and a y direction. And so now x is going to change with time and y is going to change with time. That little fraction I wrote, the top of the fraction is what variable I'm dealing with. The bottom is the independent variable, or it would be time in this example. So remember I just had dx, the change in x with respect to x. Well, then I would do the derivative of x with respect to time when I did chain rule for that.
okay. So would that mean it's 3-dimensional, how to visualize it?
It could be. In fact, if you made a graph, you would have like an x-axis, a y-axis, and a time axis kind of going out of the paper, if that makes sense. But we're not going to get that complicated in the graphs in this class. There is 3-dimensional calculus, but it's when I took calculus, it was on a quarter system. Now it's on a semester system. For me, it was Cal 3. It was the 3rd quarter of college calculus. For semesters, it might be somewhere in the 2nd semester. I don't really know where they do it in college anymore, to be honest. But it's not hard. There's 3-dimensional calculus right there, right? It's just going to be maybe x, y, and z instead of x, y, and t. But variables are just letters. You can make them anything you want. As long as you understand how the derivative works, you scale up really nicely. And then obviously this would be negative 6y squared, right? And we would write a y prime there, or how does y change with respect to x? We could write dy dx. Either one of those is fine. And then the next one would be plus 4y prime or 4 dy dx equals 0. That is implicit differentiation. And we've already been doing it. Every time we take a derivative of an equation that says y equals, what's wrong? Is my handwriting bad? Yeah, it is. Well, we're going to do more examples. I'm just kind of introducing you to the idea that every time you take the derivative of a dependent variable, that you make sure that you recognize that it is with respect to some independent variable, or not some other variable. I guess it doesn't have to be dependent and independent. It doesn't have to be. Yeah. What two? Yeah. Did I get it right?
I don't know.
You don't know? You don't know the derivative of 2?
Oh, okay, yeah, okay.
I thought you knew the derivative of 2.
Oh, okay.
So some of the things I was just talking about is right here in these bullet points. I'm not going to read it to you. Just feel free to go through those if you want to. I just told you all of them. But this is kind of the process that you're going to follow for most implicit differentiation problems. What's going to happen, similar to this quick example, you're going to want to know what the derivative of y with respect to x is, what the derivative is. So you're going to have to do this implicit differentiation and then solve that equation for dy dx. And it's really not hard to do. You put all the dy dx's on one side of the equal, everything else on the other side of the equal, and then factor out dy dx. You'll have one dy dx when you do the factoring. I'll show you what I'm talking about. Here's one. So I want to find dy dx, the change in y with respect to x, on this essentially three-dimensional graph or two-dimensional, this is a two-dimensional graph, sorry, at the point where x is 3 and y is 2, okay? So that's not too bad. Let's just do implicit differentiation. Well, this first one, xy, is a product rule, right? So the derivative of x is just 1 times y plus x times the derivative of y with respect to x. And you could write y prime there if you wanted to. It's the same thing. That's the derivative of x times y plus the derivative of y is dy dx, and the derivative of 8 is 0. Now this is a fairly simple one. If I was actually working this problem on an exam, I would go ahead and plug 3 in for x and 2 in for y. That'd be the easiest thing to do right here. But for the sake of these steps, I want to show you the factor step. Okay? I want to demonstrate this step right here. So I'm not going to plug in y and 3 for x and 2 for y just yet. Instead, I'm just going to rearrange this equation. I'm going to move this y to the other side of the equal because it doesn't have a dy dx on it. All the dy dx is on one side, everything else on the other side of the equal. So you end up with x times. Roger that. Now the reason you want to get all the dy dx's on one side of the equal and everything else on the other side is so that you can write this problem where you factor out a dy dx. It's like distributive property in reverse. Let's see, the first dy dx is multiplied by x plus the second dy dx is multiplied by an understood 1. Roger that? Are we good? And so notice what just happened with this factor step. I went from having an equation with 2 dy dx's in it. It's hard to solve an equation that has 2 instances of the variable you're trying to solve for. But then by factoring, now only have 1 instance of that dy dx. So now it's just get dy dx by itself, which is easy. Dy dx is multiplied by a parentheses, so divide by that parentheses. And now you have an expression in this problem for dy dx. Tell me any xy pair, I'll substitute the x and y's into this formula and tell you what the slope is at that tangent, that point of tangency. Bueno? No bueno. It's not too bad. Just a little equation manipulation. But all the rules we've talked about apply. Like it could be a product rule, a quotient rule. It's always a chain rule. And then all the patterns also. So let me just finish answering the question now, which is find dy dx at 3, 2. So the way some people, or you may see this written, take dy dx, evaluate it at the point where x is 3 and y is 2. That'd be 2 over 4, which is -1/2. If you see that line after a variable, it just means you're about to do an evaluation. Don't let that miss you. That's really not too bad. We need to do another one?
Yes.
Do another one? Okay. Number 2 seems awfully a lot like number 1. Can we skip it and maybe do one a little more challenging? I mean, I'm happy to do any of these with you guys. What about 3, 4? Ooh, there's a good one. 6. How about 6?
4's scary too.
4? Let's do 4 then. Oh, yeah. What? Fire away.
I don't know what to ask.
Well, okay, I have a question. They ask us to find y prime. We could actually get this y by itself. It would not be hard. And we could even just use negative exponents to... Here. This is not the way I'm going to do it, but I might if I wasn't trying to practice this implicit differentiation. I could divide both sides by e to the x. Now I got a quotient rule. That sucks. So then what I would do, I would make the exponent on e negative so that I don't have a quotient rule anymore. Right? And this is no different from what we've been doing. Now when I take the derivative, exactly what I'm going to do is write y prime. That is implicit differentiation. The derivative of y is y prime. Or you could write dy dx there if you wanted to. And then the derivative of, this is a product rule, right? The derivative of 3 is 0. I'm not going to write that term. The derivative of pi is 0. I'm not going to write that term. The derivative of e to the negative x is e to the negative x times what? -1. Everybody recognizes where the -1 came from? The chain rule, where we did the derivative of e to the something, which is e to the something, that's this. And then we have to do the derivative of the something. The derivative of, in this case, the exponent, the negative x, is -1. And then I could obviously multiply the -1 and the 3 pi to get -3 pi e to the negative x. Here. And maybe I don't like negative exponents. Roger that? It's a lot of algebraic manipulation. But let's say like, well, Dubos, you know, that seems like a giant pain in the rear end. Could we just try not solving for y? Let's just try to take the derivative, now that we understand that we can, of y times e to the x and just see if it's easier. Well, that's product rule, right? Because that's y times e to the x. The derivative of y is y prime. And that's how they have actually asked us to solve this problem, find y prime. So I'm using that notation. The derivative of y is y prime times e to the x plus y times the derivative of e to the x, which is just e to the x. The derivative of 3 pi is 0. Am I going to get the same answer? This is going to be awesome. You're going to love this. Now what, though? Get everything with y prime on one side of the equal, and everything that does not have a y prime on the other side of the equal. So I'm going to leave this term right here. It's got a y prime on it. And the y times e to the x is going to go to the other side. I'm going to subtract that. I'm not going to write subtract y e to the x. I'm just going to subtract y e to the x. Oh, my e to the x is about to leave. Did I do that derivative right?
I have a question.
Yeah.
This might be a silly question. Where would e to the x be -2? You're subtracting. Oh, okay.
If I was,
Oh, wait, never mind. They're multiplied together.
it's like 3x, right? You just move it. Okay. Now, I still have a y in my problem. So at some point, I'm going to replace y. I'm going to replace this y with what I get when I solve for that y. I don't want to have multiple instances of y or y prime in my problem. So at some point, I am going to have to rewrite this equation as y can be replaced by 3 pi over e to the x. Right? I only want to have y prime in the problem. I don't want to have any y's. I'm not going to do that yet, though. I'm just going to go ahead and divide both sides by e to the x to get the y prime by itself. So I'm going to divide this by e to the x. Divide this by e to the x. And I have y prime equals the opposite of y. Now I've got y prime by itself. Roger? No, Roger. You just don't want to leave y in the problem, so you go back to the original definition, solve for that y, and now you know anywhere you see a y, you can replace it with 3 pi over e to the x. This is going to become 3 pi over e to the x. And that's the same answer. Which one's easier? Honestly, the one on the right is probably a little bit easier, but there's something you're going to have to get comfortable with, and that's this idea that even when I solve for y prime, I may need to get extra y variables out of there. Could I have done that here on this problem? Could I have replaced that y? Could I have replaced this y with something from this equation? Think about it. Could I factor a y out of this, both of these? And then how many y's would I have in the problem? I could solve for that y and then put whatever I got right there. Roger that? Now, if I do this problem, it's not going to be an option for me to solve for y and then do a replacement, because that's going to be extremely difficult to solve for y, right? Questions? That's 3 pretty solid and challenging example problems. Let's do a harder one. Let's do a harder one. Man, I'm really liking that natural log one. So let's say this was a quiz question. Like, what would you guys try when you were taking this derivative? We could solve that for y. It would not be easy, but we could do that. So let's just use implicit differentiation. Are you going to use implicit differentiation on the problem like it is, or are you going to try to use a log property to rewrite the problem? We can do it either way. I'm just curious if you have, like, what you would be thinking. Yeah, anybody. Like, I'm looking at you because you're willing to speak. Everybody else gets a little bashful. Mr. Bracken will speak up every now and then.
I saw that I probably started crying on it.
All right. So let's leave it how it is. What is the derivative of the natural log of something? 1 over that something times the derivative of that something. So I got to do the derivative of x times y. Now that's a product rule. So the derivative of x is 1 times y plus x times the derivative of y, which we can write y prime or dy dx. I'm going to use dy dx because I don't want to mix up my y's and my y primes. And this is going to equal what? What's the derivative of sine of x? Cosine of x. Times the derivative of x, which is 1, right? What if this would have been the sine? What if this derivative would have been the sine of y? How would you do that derivative? Cosine of y times, what's the derivative of y? Y prime or dy dx. That's exactly right. So a little bit different depending on the variable that you have there. But we're right here. Am I mathematically correct? Do I have everything right? The answer is no.
What happened to the natural log?
What is the derivative of natural log?
1 over x.
Where's the natural log?
Natural log of x, y.
No. What is the derivative of natural log of something?
1 over that something.
Yeah. The derivative essentially takes the natural log out and replaces it with 1 over the something.
Yeah, but if it's product rule, it would be added in the second part of the problem.
I hear what you're saying. I'm going to try to answer that with a different function and see if this makes sense. What is the derivative of tangent of 4 theta? I'll help you.
Secant squared 4 theta times 4.
What happened to the tangent?
You took the derivative of it.
What happened to the natural log?
There's product rule.
So is this. It's 4 times the derivative of theta plus the derivative of 4 times theta. But what is 0 times theta? Yeah, so we don't write that. Same thing with natural law. But am I 100%? I am not 100% accurate. There's something I've done completely that I've left out.
Parentheses on the cosine of x?
Parentheses, yes. On the x is optional. Right now, this, come on, Richard. Only the y is multiplied by the derivative of the natural log. That's wrong. The whole product rule piece, the derivative of all of this has to be multiplied by the derivative of natural log. Don't be lazy with the parentheses.
Can you also just put parentheses on top of the x and y, like in the numerator?
Ooh. Ooh, that's slick. The question is, could I write it like this and just go ahead and multiply the parentheses by 1? And then I don't have to write the parentheses because the top of the fraction kind of serves as the parentheses. Yeah, 100% you can do that. But then, and it's not too hard from here. Just you want to get the dy dx by itself. on the left-hand side, what's the first expression that you have to get rid of? You can't subtract the y because the y is in top of a fraction. Can you get rid of the x times y that's on the bottom of the fraction? Yeah, we're just going to multiply both sides of the equation by xy. We're going to do this. To cancel here. I'm going to put the xy in the front of cosine so that nobody thinks that the xy is inside of the cosine. Like when Mr. Bracken was talking about using these parentheses. This is just a little insurance so that I know I don't accidentally put that xy. And then to get dy dx is 2 steps from here. You can divide by everything by the x in front of dy dx, or you could subtract the y to the opposite side. I'm going to subtract the y to the opposite side. And then to get rid of that times x, I just divide by that x. That is a fairly large amount of algebraic manipulation. Some people say the hardest part of calculus is algebra. That's a pretty good example of, it's not really that hard, but it's a lot. Good? No good. My question, what I worry about is can you get that step? Right, like that is implicit differentiation. It's the basis of what we do in calculus. So can you get that step? After that, it's all algebra. Do we need to do any of these other ones? Oh. Do you know what they're asking you in what you're being asked in number 8? Oh, we got time. We got time. You okay, Miss Haver?
Yeah, it just everyone like moved at once. I thought it was time to go.
So you haven't seen it a whole lot, but do you know what that notation means?
The derivative
Of the,
y squared. Well, no, it's hard to phrase, but I know what it means.
okay. Here, let me write it a different way. Do you know what this means?
Yes.
What? The derivative. What does this mean?
Second derivative.
So this is what the second derivative looks like using that Leibniz notation, or whichever mathematician it was that used this one. That's the second derivative. So let's go through it. Let's do what?
I said I don't like this notation.
Well, you don't really have to use it yet. When we get into the second semester with integrals, when we set up integrals, sometimes it might be useful to use this stuff. But let's find the first derivative. What is the derivative of cosine of something? Negative sine of something times the derivative of that thing. Well, what is the derivative of y? And the derivative of x is just 1. Can we get that dy dx by itself? Yeah. All we have to do is divide by negative sine of y. So let's do that. Dy dx equals negative 1 divided by sine of y. Now that's the first derivative. We got to do a second derivative. Do you want to do the derivative on -1 over sine y, or do you want to do the derivative of negative, what is the reciprocal of sine? So which of those do you want to do the derivative on? You want to do the quotient rule? You want to do the derivative of cosecant? Cosecant for sure. So here we go. Let's do the second derivative of y with respect to x. We've got a negative out front. What is the derivative of cosecant of something?
Oh, that's secant,
You got the cos, positive or negative? Oh, negative.
times cotangent.
Negative cosecant times cotangent. Now, don't write it like this. This is wrong. You can't have a trig function without an argument. You have to have the something. You have to have the cosecant of y times cotangent of y. And then when you multiply those two negatives, you get a positive. I would stop there, but I want to review something real quick because I don't think I put it. Do you know how to solve this equation? I'm going to spread this out a little bit because I need to write some things. Do you know how to solve this equation for y? Now, the reason I'm doing it is because some of you guys have seen this before. Some of you may have never seen this before. Do you know how to get the cosine off of the variable? Some people call it an arc cosine. Some people call it a cosine inverse. There's two ways you can write it. You can write it like this, with a little -1 power right here. That cosine with a -1 exponent, the inverse cosine, is the mathematical opposite of cosine, just like adding is the mathematical opposite of subtracting, or multiply cancels divide. But if you cosine inverse the left side of the equation, right? Another way to write that cosine with a -1 is called an arc cosine. Some people call it an arc cosine. I'm just going to use the little -1. But what happens is these cancel. And now y is by itself. And then what I could do, I could come down to my equation, if I don't want to have y's in my equation, and write this as the cosecant of the cosine inverse of x times the cotangent of the cosine inverse of x. And all the cosine inverse of x is, it's doing the unit circle in reverse. If I asked you for the cosine of pi, you know the cosine of pi? The cosine, close. Change your sign. Yeah. The cosine of pi is -1. The way the cosine inverse works is I tell you the point, I would say, well, the cosine inverse of -1 is what angle measure has a cosine value of -1? The answer to this would be pi. All the inverse does is switch the argument in the answer. It switches the x and the y, if you will. More on that after our next test, because we're going to do derivatives of inverses. It's a tricky one. Good place to stop. Great place to stop. Any questions, though? You like you have a question. Fire away. Ms. Skinner, you got one? Question?